Welcome to module 31 of database management system. This module and the few following it will be on transactions. So, we have so far through the modules that we have done, we have so far looked at first the schema of a database system, which is the plan, the layout of how the data will be organized. Then we have looked at if the data is populated, then how we can query, how we can manipulate the data. We have looked at how the data is actually physically stored and how it can be efficiently accessed through different mechanisms in the storage. Now, we will focus on the actual execution time. We will focus on what goes on when the data in a database system is accessed, it is read, locally modified and then written back. In a very simple terms, this is the operation that keeps on happening in the database systems, which we will identify, which we say are transactions. So, this is what we had done in the last week, talking about index, and we now start with the understanding of this concept of transaction, and we explore various issues related to concurrent execution of transactions. So, we will explain in more detail what these mean, and these are the three topics that we will focus on in this module. So, let us first take a look at what does a transaction mean. So, we say a transaction is a unit of program execution that accesses and possibly updates various data items. So, it reads, possibly makes some local changes and then it writes it back. So, here is an example of a transaction. So, without the unnecessary details, what it looks at, there are two accounts, account A and B, and we want to transfer $50 from account A to account B. So, we need to debit account A by $50 and then credit account B by $50. That will achieve the transfer. So, to start this process, we first need to know what is the current balance of the account A. So, that is done by read A, the first instruction. Then, so A, after reading, A has come into a local buffer, into a temporary which exists in memory. If the current balance was $200, then that has not changed, that remains to be $200. A has become is a local variable which is taken the value $200 now. So, we locally change it, we debit $50 from that. So, A becomes $150 and then we write it back. So, in the account balance where it was $200, it will now become $150 with this $50 debited. Then we have to do the credit process to the account B. So, in the fourth instruction we read B. So, let us say the current balance of account B was $300, then read B will make the temporary variable B as 300. We credit 300, that is we add $50 to that, it becomes 350, and then we write B onto the account B's balance. So, account B's balance will now change to $350. So, this whole sequence of 6 instructions is called a transaction, and as you can understand that to achieve our target of transferring $50 from account A to account B, all these 6 instructions have to execute in this order, so that we can get the desired results. Now, the question is, so this is pretty simple, this is like very simple low level program, but there are two main issues that we have to deal with. First, what is the guarantee that once the instruction 1 starts, what is the guarantee that it will continue up to instruction 6? There may be some failures in between, the disk may fail, the hardware may fail, the system may crash. So, what will happen to the state of the database, what will happen to the values that exist in the database, what will happen to the target operation that we wanted to achieve through this transaction if such failures happen. A second issue is we need multiple transactions to execute concurrently. What it means that suppose I am working on a net banking, updating my account, I am making transfers to another party whom I need to pay. At the same time, several other people are also doing operations on their accounts, respective accounts. Lot of other operations might happen from the database itself. For example, while I am making a transfer, at that same time the database may be crediting some quarterly interest to my account. All these transactions actually execute concurrently, which means that they all are independently executing, they use the same CPU, but they achieve the result at the same time. So, it is not that the transactions are actually happening on separate machines, the transactions have to take effect on the same database. So, they have to occur in a concurrent manner, that is what we say is a concurrent manner, because they occur together. And while this is going on, how do we ensure, but there is one CPU. So, the CPU is executing these instructions in some order. So, how do we ensure that this in the face of such concurrency the transactions will still give me correct result. So, these are the two major issues for which we are going to study about transactions and what we in general say the transaction management systems. So, we first set the targets, we put some required properties of a transaction. The first requirement is atomicity. Suppose again just look at the same transaction. Suppose the system crashes, there is a system failure after the first three instructions has happened and fourth instruction was about to happen. So, what will happen? Already the account A has been debited by $50 and account B has not yet been credited with that $50. So, simply at this point if the transaction, if the system failure happens, then simply $50 will disappear from the system, it will not exist. So, the basic requirement is that once a transaction start, it should either completely happen, it should either do all the 6 instructions as in this case, or it should do nothing. So, there is a all or none kind of requirement is there, that is what we say. It is like, so transactions in a way are indivisible or atomic, and this is the atomicity requirement. The second requirement is called consistency requirement, that is as the transactions are making changes to the database, through these changes the integrity of the database, the consistency of the values should not get affected. So, if there are certain specific integrity constraints, we have talked of primary keys, foreign keys and so on, and there could be implicit domain integrity constraints. For example, in this accounting case, if we are making transfers, then while making a transfer from account A to account B, the sum of the balances in account A and account B before the transfer and after the transfer must be same. So, money should not disappear, neither should it get generated. So, what we assume that a transaction when it starts to execute, it must start in a consistent database, which is correct in every respect. During the transaction, there may be temporary inconsistency. For example, if you look at instruction 4 or instruction 5, at this time the account A has already been debited by $50, the account B has not been credited by that $50. So, if you at instruction 4, if you try to see what is the sum of the balance in account A and account B, you will see that sum is $50 less. But when the transaction completes, it completes the instruction 6, then again the sum will be same as it were at the beginning. So, at the beginning of an execution and at the end of a successful execution, the database must be consistent. In between, there may be transient inconsistency. So, this is called the consistency requirement. The third is again, first look at the example. The same on the left is a transaction T1, which is the transaction we have been talking of, and suppose there is another transaction T2 which happens concurrently. If it happens concurrently, the transaction T2 has, let us say, 3 instructions: read A, read B and print A plus B. So, it tries to read the balance of account A and B and prints their sum. Obviously, if the transaction T2 is allowed, these 3 instructions of transaction T2, if they are allowed to be executed between instruction 3 and instruction 4 of transaction T1, then T2 will print a sum of A plus B, which is $50 less than the sum of A plus B at the beginning. So, it will appear as if there is some inconsistency that has happened. So, the isolation requirement says that when transactions occur concurrently, the net effect of the transactions should be as if they happened, either first T1 happened and then T2 happened, or first T2 executed and then T1 executed. Even though they may execute in a concurrent or mixed manner, the result of such inconsistent state of the database should not be available to the other transactions. So, this is called the isolation requirement. So, that transactions need to be isolated appropriately, so that they can, obviously if they execute serially, then the isolation is trivially satisfied, but that will mean that your throughput, your performance will be very low. So, we need transactions to happen concurrently, but the isolation must be satisfied. The fourth is called the durability requirement, which says that if a transaction has finally completed successfully, then the update, the changes that the database that has been made by the transaction, that must persist even if there is some software or hardware failures in future. So, once this transaction of transferring $50 from A to B has successfully completed, with the 6 instructions having been executed and the money having been transferred, that should persist even if subsequently some errors, some failures in the database would occur. So, it must be, the changes must be durable. So, these 4 properties are together called the acid properties of a transaction system. So, acid means A for atomicity, that either all operation of the transaction are properly reflected in the database or none of them are reflected. Consistency, C for consistency, execution of a transaction in isolation preserves the consistency in the database. The isolation requirement, that if multiple transactions are occurring concurrently, transaction Ti or Tj are occurring concurrently, that is some instruction of Ti happen, then some instructions of Tj happen, then some instruction of Ti again happen, and in this manner, even then the final result should look like as if Ti has happened followed by Tj, or Tj has first executed followed by Ti. The isolation, I for isolation, and finally durability. Once the successfully transactions have completed, the changes in the database should persist. So, A, C, I, D, the acid properties are the critical properties of the transaction system and must always be satisfied. Next, what we look at is, as transactions go through each and every instruction, the transaction happen to be in one of the different states. So, while the transaction, as soon as the transaction starts and starts executing, starting from the initial state, it is in an active state. So, consider this same transaction, it is done read A, it is in active state, it has decremented A by 50, it is in active state, and so on. So, as long as it is executing, it is in active state, unless it has, okay, first let us talk about success. So, once it has executed the last statement, last instruction, that is instruction 6 here, it is in a state that is called partially committed. So, it has been able to successfully complete all the instructions, or it might happen that during being in the active state or being in the partially committed state, some errors has happened, so that the normal execution cannot proceed any further. Then the transaction comes into the failed state. A transaction which is in the failed state will eventually get aborted, because it is not known when the failure has happened. So, naturally at the time of failure there could be inconsistency. Failure could have happened in the fourth instruction in this transaction, and as you have already noted that A has already been debited by $50 and B has not been credited that $50. So, it is in an inconsistent state. So, if the transaction is in a failed state like this, then we need to roll back, we need to undo the changes that we have done, we need to credit back the $50 that was debited from A, so that we can reach a consistent state. And once we have done that, once we have done this rollback successfully, the transaction goes to an aborted state, that is it could not take place, and after that you have two choices: either you can restart the transaction or you can totally kill the transaction, do not do it at all. Depending on different situation, that choice is made. In the other case, if it were partially committed, then all instructions had completed. Now the bookkeeping and other actions were required. If there is some failure during that time, from partially committed it comes to failed state and then goes to abort state, as I have already explained, or it actually commits all the changes correctly and it has completed successfully and it goes to a committed state where the transaction has successfully finished. So, every transaction will go through this state. At any point of time, a transaction will be in one of the states, and depending on the status of execution, it will continue to remain in that state or will change state. So, this state transition diagram for transactions are very important, and you must thoroughly understand what is happening and remember this particular state transition. Okay. Now, let us look into the actual concurrent execution situations. So, in the concurrent execution situation, what we have? We have multiple transactions that run at the same time on the system. So, that will the advantage is it will increase throughput, it will increase processor and disk utilization. For example, when one transaction is doing some operations on the CPU, some internal computations are going on, the disk can still be accessed by another transaction to read or write some values. So, the throughput will increase, and also the average response time will reduce, because there may be a short transaction which, if it were serially done, then it will have to wait for a very long transaction which may already been executing. But if we allow concurrent execution, then in between that long transaction, few cycles may be taken to execute the short transaction and the average response time will improve. So, that is our basic requirement. Naturally, we need to do this in a controlled manner, so that we ensure that the ACID properties, the consistency of the database and the ACID properties are maintained. So, for doing this, we create what is called a schedule. A schedule is a sequence of instructions that specify the chronological or the time-wise order in which instructions of concurrent transactions are executed. So, what will the schedule have? Schedule will have, for a set of, it is defined for a set of transactions, and it must consist of all instructions of those transactions and in a certain order. And what is the basic requirement? That in this schedule, in this ordering, the original order of instructions in any of this given transaction, given individual transaction, must be preserved, but the instructions from different transaction can be intermixed in between to prepare the schedule. So, a transaction that successfully completes its execution will perform what is called a commit instruction. We will more specifically say what is commit. A commit instruction, which means successful completion, as the last statement, that should be the last statement. If the commit is not given, by default also transactions which have executed successfully are assumed to have executed commit, or if the transaction fails to successfully complete the execution, that it will do an abort as the last statement. Okay. So, let us take an example. So, again we are going back to the same example. So, we have two transactions T1 and T2. T1 transfers $50 from A to B, as we have seen, and T2 transfers 10% of the balance from A to B. So, one transaction debits $50, one transaction debits 10% of the account balance of A to B. So, if they are serially executed, as you can see here, we are serially executing them as in. So, first your whole of T1 is executing, and once this has committed, that is successfully ended, then T2 is executing. So, at the beginning, if we assume, this is just an assumption, if we assume at the beginning that A had $100 and B had $200, then the sum was $300. So, the A is read, $100 is read, then it becomes 50, then you write this A. So, when you are here at this point, you can see this is what you will have, because A has changed from 100 to 50 because you have debited. B, nothing has happened on B. So, sum is 250. So, you can see that is why I have shown different colors. You can see at 250 this state of the database is temporarily inconsistent, because the sum has become different from 300. Then it reads B, it reads 200, adds that 250, it writes B. You come to this point where after this write, when the commit is happening, after the writing this B, then T1 has actually completed and $50 has got transferred to account B, and the sum is again back to 300. So, consistency is preserved. Then transaction 2 starts. So, A is read, $50 is read. In temporary, you compute 10% of that $5, you decrement A by $5 and write it back. So, when you have written it back, you write back $45. Again, naturally the sum becomes $5 less, the $5 that you have kept in this temp, and this becomes again transitively inconsistent in the process. Then you do the read B, add that temporary $5 back to B, and then you finally, when you write B here, you write back from 250, you have added $5 to 255, and again the sum becomes 300, you are again back to the consistent state. So, you can see through this process that when transactions actually happen in a serial manner, this is how things will go on. So, which is quite understandable. So, let us move on. So, this is a different schedule, you can see, but this is also a serial schedule. Here what we have assumed that all instructions of T2 are done first, then all instructions of T1. I am not going through each step. You can see what are the consistent and temporarily inconsistent states of the database, but at the end the database is in a consistent state, and you can note that now the end value of A is $40 and end value of B is $260. In the previous schedule, the value was $45 and $255. These two are different, but both of them are actually correct. Both of them are consistent, because when things happen in this distributed manner, we have no control in terms of whether first $50 should be debited and then 10% should be debited, transferred, or whether first 10% should be transferred or $50 will be transferred after that. Either of that is a correct consistent state. So, the different schedules might give you different results. That is not of any concern, because both of them are possible valid results, but the question is it must finally have a consistent state of the database. So, both of these are consistent. Now, take an interesting example where schedule 3, wherein here if you look at carefully, there are few instructions of T1 which are executed, and then in the temporal order few instructions of T2 are executed, then again T1, then again T2. So, the instructions from two different transactions are getting interleaved, and this is what the execution status would be. So, you can see that when you are when T1 writes A, this is where you are, $50 has been debited. Then when T2 writes A, subsequently another $5 is debited. So, it becomes 45. So, then you have T1 again executing and adding B onto that, and by that it is not only that it has gone into an inconsistent, it was already in an inconsistent state, but that was transient, that was temporary. But now the transaction T1 has totally completed, it is completed its execution, it is at its commit, but your database is still in an inconsistent state. So, this is something which is possible because you are doing an interleaving of the instructions of the two transactions in the schedule. But once you allow the rest of the transaction B, this part to complete, that is B gets updated and you reach here, and that also has committed. So, your schedule comprised of transaction 1 and transaction 2, when both of them have completed, you have again reached a state which is consistent. And if you look at the results of what you have achieved, you will immediately identify that this doing the transactions according to schedule 3, which is interleaving in this manner, is equivalent to this in this manner of interleaving is equivalent to doing them according to in this manner, which is schedule 1. So, you have got a schedule which is equivalent to schedule 1, and it is therefore, so this is just an example to show that it is actually possible to interleave the instructions of two transactions and create a schedule which will still, which might in the process have transient or even inconsistent commit states of the database, but finally when the schedule ends, it is possible that it will bring you to a consistent state. Now, look at again for those transactions, look at a different interleaving, a different schedule, again T1, T2 are involved, but you have now tried to interleave them in a different order. So, earlier the interleaving was done after T1 has done write A, here it is done after A has been the locally debited by 50, and then this part is done and then the write is happening. And now, if you go through the steps, I will leave it as an exercise for you in schedule 4. Now, if you go through the state, you will find that when transaction T1 commits ends here, you have an inconsistent state, and finally, even when the schedule ends that T2 is committed, there is you are in an inconsistent state. Somehow the sum of A and B, which was 350 has become 300 has become 350. So, $50 has got generated. So, this is, so you can see that if you interleave the transactions, then it is quite possible that the transactions will may or may not actually give you a consistent database. So, here in this module we have understood the basic task that a database performs, database executes, which is in form of a transaction, and we have seen that they must satisfy a set of properties typically called the ACID properties, and atomicity, consistency, isolation and durability must be satisfied. And when the transactions are executed in concurrent fashion, we improve the throughput, but the concurrent execution of transaction raise issues of serializability, that is the concurrent execution, that the interleaved schedule of instruction of two or more transactions can give rise to certain effect which violate the ACID properties, and those need to be addressed. That certainly inconsistent database is certainly never acceptable, and so that is the basic problem that we have identified, which we will have to address in the coming modules.